Let G be a group such that every element of G is equal to its own inverse. Show that G is abelian. Okay, so we have that G is a group, and let's just remember what is a group. So a group is a set together with a binary operation such that it's closed, meaning you take any two elements of the group, perform the binary operation on them, and you get back something in the group. It's associative. That means that when you multiply, you can move the parentheses around. And I say multiply, but I really mean perform the binary operation. I'm going to refer to it as multiply, but it could be any binary operation. Then we have the identity element. So that means that there is some element in this set, and usually you refer to it as E, such that A times E equals E times A, which equals A, where A is any element in the set. Then we have inverses. Every element that's in this group must have an inverse, and usually you denote it as A with a little -1. And that means that A times A inverse equals A inverse times A, which equals the identity element. That's what an inverse does. You multiply it by the element, A inverse times A, it gives you back the identity. And then we also have this word abelian. What does it mean to be abelian? Well, if something is abelian, that means A times B equals B times A for any A and B that are in this group. Okay, so let's, before we do the proof, try and figure out what we're going to do here. So every element is equal to its own inverse. All right, well, that means that A must equal A inverse, and that means that B must equal B inverse. Well, that's great, but how am I going to get this expression here? That's what I want. AB equals BA, that's my goal. Well, it's probably going to involve something in using A and B. I have A and B individually, but what about AB? So AB, well, I know AB inverse must equal AB because A times B is an element in the group. The group's closed, so AB inverse must equal AB. But I also know from group properties that AB inverse, that can be rewritten as B inverse A inverse. But, okay, I think I see it here. So AB inverse equals AB, and AB inverse also equals B inverse A inverse, but that's just B times A since every element equals its own inverse, and then AB equals BA. Okay, I think we're ready for a formal proof. To start out, we should probably say something like, let G be a group such that every element of G is equal to its own inverse, just something to set the stage here. And again, make sure you always use complete sentences in your proof. Next, we should probably say that we have two elements, A and B, that are in G. And now, since every element equals its own inverse, I know that A inverse has to equal A, and B inverse has to equal B, and AB inverse has to equal AB. But I know that AB inverse equals B inverse A inverse by the group properties, and since every element equals its own inverse, I know that equals B times A. And I'm pretty much done. So AB equals BA, and G is abelian. It's a pretty simple proof.